So both of you, thank you so much for joining us and doing this as well on the podcast. And I think what I really love about this conversation is that I think we're in a time where I think we need a lot more interactions like this, where people with opposing views are willing to come together and debate and things like that. And I think it is a very interesting time where we can do this. But I was thinking maybe just a good way to start this would be maybe just for yourselves, just to introduce yourself to the audience as well, a bit about your background and sort of things like that. You want to go first, Dave? Yeah,
I'll go first. Well, I'm Dave. I've been a researcher into topics of the truth for about 15 years now. Looked into various aspects of the truth, starting with 9/11 and going on to various different topics from there. So I got into the flat Earth in the summer of 2014. Just come across a strange video talking about weird experiments, and it also told me about the curvature calculation, and I was a bit surprised at what that calculation was, so I went out and tested it and found that I could see way more than I'm supposed to be able to see, and that's what started me off.
Yeah, well, over to you, Pierre.
Yeah, so I'm a postdoc at the University of Sussex. I'm very happy I'm here. This is I must say, this sort of podcast is probably not something that I would watch myself as a scientist and as a person, but of course this means that this is very different public, from the one that I'm interacting to, and of course that makes it way more interesting. So I'm actually very honored to be here, and I think as you said, we need to have more of these interactions. So for me, I am a researcher at the University of Sussex. I've been here for a few months now, since May, and I study particle physics, which is the sort of the fundamental constituent of nature, the one which we can't go any smaller by by observation, essentially. So we have, there is a theory which is essentially self-contained, which is sort of what I do in my daily work, try to see and to understand this theory. And this theory is called the standard model of particle. And so we are trying to essentially measure the free parameters of the standard model with experiments like the Large Hadron Collider, or some experiments I'm working on actually, which is on neutrinos. This is what I am.
Cool. So maybe Dave, I was over to you, and I was just going to ask you maybe what some of the sort of the leading points in your mind why you think the Earth is flat.
Okay, leading points. Well, the first most obvious is the complete lack of curvature. No matter how much we try and find the pesky curvature, we can't find it. As I said, I mentioned the curvature calculation, which on a 25,000 mile circumference should be 8 inches per mile squared. That's the amount of drop that you should experience. So armed with that calculation, you can go out and if you have a landmark a known distance away, preferably over the sea, because obviously there's nothing in the way, you can do sighting experiments to see how much you're supposed to be able to see, and I guarantee you'll see much more than you're supposed to be able to see. So between that and the gyroscope, that's my pet one. The gyroscope has a property called rigidity in space. That means once it's set spinning, it will stay in its orientation no matter what you do with it, regardless of gravity, regardless of where it is on Earth. It will stay in its original orientation, according to space. So you get aircraft have a gyroscope. They always have a mechanical backup gyroscope in their artificial horizon. So how it works, very, very simply, is before the plane takes off, they're on a level surface. They spin it up so it gives you the true reference to the ground. So once that reference to the ground is set, then they always know where the horizon is, even through thick cloud. It's not because, as the plane sort of does its manoeuvres, the gyroscope will stay in its original orientation. Fundamental principle of gyroscopics. So if a plane is doing, let's say, 4,000 mile trip, I think that's something like 90 degrees. Maybe it might be, I can't remember, but it's probably about 90 degrees, or 60 degrees, I think it is, of arc that it will make over the round Earth. So the artificial horizon should start to roll backwards during straight and level flight, but it doesn't. It tells you that a plane is flying over a plane. Now, people have said that gyroscopes have these things called pendulous vanes, which correct for the curvature. But when you actually look into what these pendulous vanes are there for, it's to stop the other property of a gyroscope, which is called precession. And precession can be induced mechanically by sort of, if it's a vacuum system, by uneven air or particles of dirt in the air, or it can be induced if you do too many manoeuvres. You get to a point where the gyroscope starts tumbling. So they invented these pendulous vanes to stop it tumbling. It doesn't correct for curvature. So that's it. It's those two. I think I've got to add as well, while I'm on that subject of planes, is that planes, its attitude, an attitude of a plane, and straight and level flight, is determined by the air flowing over the wings. Nothing to do with gravity, nothing to do with the surface of the Earth. If the air is flowing in the right way over the wings, the plane will fly straight and level. If you let go of the yoke of the controls, the plane is supposed to fly straight and level, but sometimes it doesn't. So they have a thing called a trim wheel. So they trim the the control surfaces, so that the plane will fly straight. Okay, so if a plane is flying straight and level over a curved surface, it will start to gain altitude, and the pilot would have to nose that plane down to keep it straight and level. But no pilot ever has to make make changes. They never have to nose down, and the plane will not automatically follow the curve of the Earth. It will fly straight and level according to the air flowing over it. That's it.
Yeah, very interesting stuff. So just over to you, Pierre, as well. In relation to sort of what, in relation to the same question I said to Dave, but over to you in terms of what's the key points in your mind why the Earth is, why you believe in the Earth is round. Sorry.
Well, I mean, it's not that I believe in. It's really because it is. I mean, it's not because, I don't want to say that in a sense of, sounding a little bit pedantic, but it's because there is many observations from many different people that are saying the Earth is round, right? So I have here, I've listed actually the top spatial agencies around the world which have taken picture of the Earth. So there is the Chinese National Space Agency, the ESA, the European Space Agency. So if you look on, newspapers, on internet, you will find some pictures by national newspapers that have a picture of the round Earth, and that's coming from different sources, and I think this is just a good enough example, right? So a good enough evidence. So there's the Indian Space Research Organization, the Japanese space, the JAXA, NASA, the Russian equivalent Roscosmos. So I think this in itself is probably a good proof, right? I mean, I don't really there is. Yeah, it's a bit. So for the fact that, you know, it's because like well, yeah, I mean observation essentially, and the self consistency of all that we know is probably what is the best answer. So we don't observe any object. If we look through a telescope, there's nothing which looks flat in the universe, and that is, you know, that would be very weird that, you know, once in a billion thing that, well, maybe not billion, but like in a million thing, then we have to have something that says the Earth is different from everything else because it's flat, and that would be, you know, we would have to explain what if the Earth was flat, then there would have to be a theory why every single object that we observe in the cosmos is round, and well, yeah, I think this is already quite a very powerful statistical way of doing it, right? We have many different. If you look through a telescope, you will never see something flat on the in the sky, which is already, you know, like as far as science is concerned, you know, this is very powerful, right? To have to say, oh. So that means we would be in a very different place, right? We would be in a place where you know, it's very it would be very particular.
I was just going to say before I jump in.
I'm sure you have some points on that later.
Yeah.
Did you?
I mean, I was just going to dive straight in now, and I was actually going to, because I just want to give you a bit of time to sort of introduce yourselves to the topic yourselves, what you think about it. But I would love to now just basically just open it up and just sort of get straight in the deep of it and allow yourselves to, maybe if you have any questions for Dave, if you have any questions for Pierre.
Could I ask you, Dave? Dave, what would you make of what Pierre says there about the various different space organisations that have taken photos of the Earth and it is actually showing a sphere?
Right, well, the first and most obvious question is, why does every single photograph of the Earth look different? If you put them all together and look at them, every single one looks different. The answer to that is with a guy called Rob Simon, who actually works for NASA. Okay, and his job, as he describes it, and you can find this on YouTube, is creating images from data. Yeah, so he gets a load of data, and he creates a picture of Earth from this data, and you'll see that he says, you know, I have to I take the clouds out, and I have to put a layer over it to simulate the atmosphere. I have to put something called a specular highlight, where it's where the sun would reflect on the sea. I have to, you know, give it depth. I have to make, and he says how he artistically creates this image. It's called the blue marble. Yeah. And he says, I don't know what it's supposed to look like. I'm not an astronaut. I've never seen it. Right. But this is what I think it looks like. Yeah. Now I can tell you that in every single one of these space agencies, there's a Rob Simon creating these images from Photoshop. And I think the famous line he says, it is Photoshop. It has to be. Yeah. So I'm sorry, every single one of these so-called images from space, right, are not photographs. They're composites. They're made up CGI, and doesn't matter what space agency that who's producing them, they're all getting in on the bandwagon of taking public money for, you know, and giving lies for it.
Yeah. So I mean, if we look at what we have in front of us, and we would take different cameras, you know, take this one, take your phone, take somebody else's phone, take a big DCR, Nikon, super smart, cool one, then we would get a different image. I think this is really clear, right? So that means technology and what exactly we're recording on the tape is going to make, you know, the image different. And I think this is
different.
Really
how?
clear.
Different how?
As in the number of pixels, the internal resolution, the whatever objective you put on
Colors?
What do you mean?
The colours be resolved differently.
Yeah, the colors be resolved differently
Size
because
of continents change.
huh?
Size of continents change.
Well, it's different space. Well,
Different space, different.
in different you know, you could take it in around different place, and then you know the right. This is my hand, right? If I look at it in this way, then it will look different, and I'll take a different picture.
No,
if
I didn't say
like this.
different in orientation. I said different size. There's.
But it looks different in the size, right? Like if I have it very close and if I have it very far.
Yeah, but in relation to the Earth, the size of the Earth, yeah. We've got multiple pictures of the United States, for instance, where they're different sizes on the Earth. Yeah, we've got things like pictures of Australia, yeah, from daytime and nighttime with exactly the same cloud formations above it. You know, like clouds do not move apparently. I particularly have a picture, Galileo, which is taking the 25 shots over 25 hours showing the rotation of the Earth. Right. Well, there's some very particular cloud formations on it, yeah, that don't move over 25 hours, yeah. But I've also found a picture taken supposedly of Antarctica from space with exactly the same cloud formations, yeah. Which they're using a cloud map. So I'm sorry, what?
So if I had to do this, right? If I had to make clouds, then I would use a random number generation, and there would be no possibility of having the exact same clouds. What I think is happening is, yeah, it looks quite similar, but to be honest, I also have the impression, as you said, those images can be photoshopped, then I think you might be looking at Photoshop pictures as well.
Sure, but go to NASA, download their big blue marble image, and then you'll find on that image what they call clone stamped clouds. Yeah. So in Photoshop you have a tool called the clone stamper. Yeah, where you sample a part of the picture and you can stamp it in various places. Yeah. So you'll find that most of that image is made up of clone stamped clouds. You can get it, download it yourself and find it. You know, nature doesn't create sort of multiple versions of the same cloud.
Yeah. So
sorry, I was just going. You go ahead, right, Ed.
I just also the other thing about the blue marble. So I don't know what is blue marble, but there is also a whole part of science which is very important, you know, for me and for the weather forecast and all of this, is predictions and model building, right? So I'm not sure what is exactly blue marble, Matt, but I have this impression that you're talking about some people trying to replicate, you know, the behavior of the Earth, the behavior of like how clouds are moving, and how, you know, sort of like the system of the Earth, right? And that is, you know, at the end that gives us something which is probably really close to what we know as the system of the Earth round us and something like that. But this is just a model simulation, and the reason why we do that is we want to like try to infer what is going to happen, you know, for weather, what is going to happen for climate change and things like that. So this is, you know, there's, you know, science is about trying to understand what we see, right? So there's the whole part which is observation, and we have to observe what we see and taking data. But there's another part which is we have to predict which model can actually fit this data, can make it look like what we are seeing, right? And this is what the whole area of model building. And I'm not surprised that there is somebody like that in NASA who is actually whose job is actually to like make the Earth, create a simulation of the Earth, right? Because this is what is being used. We want to have that, right? We want to have this sort of things and have a complete understanding, because if we can simulate it and then observe the exact same, you know, and take a picture and take the exact same picture as what we've simulated, then that means we have a complete understanding of the system.
We're not talking about a simulation, okay? in 1972, the only image that's supposedly a photograph of the Earth, was taken by, I think it's Apollo 17, right? It's the only one that is ever acknowledged to be an actual photograph. Now there's footage from Apollo 11 showing how they faked, seeing the Earth as a ball in space by turning off all the lights in the cabin, having the porthole in the spacecraft, be the circle of the Earth, the Earth filling up the whole porthole, and then putting a piece of card in to represent the Terminator, That was them faking a photograph of Earth from space. Okay, so the 1972 image is suspect. Okay, so NASA basically says that every other image, including the blue marble, which is just a photograph, it's not a simulation. It was just there to create a photograph, supposedly. Every other image that NASA puts out is CGI.
But it's not only about NASA, right?
Well,
there's Chinese,
all
European,
the others
Indian,
too.
Japanese.
All of the others too. They're all getting in on the
Why
act.
would there be this sort of conspiracy? What would these people gain to do this sort of things?
On the really base level, okay, NASA gets something like 58 billion. Is it 58 billion a day or something? Oh no, 52 million a day. $52 million a day. Okay, that's enough of a reason to do these things just on its own. There are other reasons for it, but that's that's the one that most people can actually understand. If you're getting $52 million a day, right? Wouldn't you fake it if you can convince people to give you $52 million a day, and all you have to do is give them photographs? Yeah.
Is that?
Well, I mean, because this is getting a little bit into politics, so I just want to take a step back because, right, this, what would it prove for me to convince you of the inverse, right? Because if you told me, right, well, we have, and I'm going to look those up, right, the gyroscopic effect, etc. Although I doubt that this is going to, well, okay, I can explain this later. But if you were to come here and have sort of explanation why, for example, we don't observe anything which is flat, why is the sun shining, where does it get its energy from, this sort of things, then I would be ready to be like, okay, maybe the Earth is flat, right? But the thing is, and that is because what I believe is science is falsifiable, right? So this is from this is maybe a bit pedantic, but this is from Karl Popper, all right, which is a philosopher, and he wrote that in The Logic of Scientific Discovery in 1959, and so it's like science has to be falsifiable. So sometimes we get it wrong, and then somebody comes up with a great idea, and then the whole paradigm, the whole way of thinking of science just changes, right? But that NASA fake photos doesn't really change the way science is. Nature doesn't really care about NASA, right? It's not like all this is like, this is all upstream political. All of this doesn't really change the science of it.
NASA's not there to change science, though. It's there to change the minds of people. That's it. It's not there to change science. Well, sorry to interrupt.
This is kind of what I wanted to say, really, because you're saying the lack of curvature, right? Okay, let's say you cannot see. You're talking about this, Well, I'm assuming is like you put something which is of known height, and then you go somewhere far, and then you try to see whether you can see this one with spectacles or something. Is that?
It's not so much a known height, but see the bottom of it, for instance.
See the bottom of it.
Yeah.
Right. Well, I mean, at which height do you do your observations? At, how is the sun reflecting? All this sort of thing matter, and you just have to have it. Like you have to go. This is not about. You're not trying to measure the actual radius of curvature, right? You're trying to measure whether the Earth is round or not. It's a different problem, right? So if at any point you go further enough and then you don't see the stick anymore, then the Earth is round. Is that?
Well, absolutely not, because you can do an experiment yourself. Get a camera, place it on the ground, yeah, and on a flat surface like a basketball court or something, yeah. Walk away from that camera, and you'll find that your legs disappear, and up to your knees will disappear.
No, but I mean,
that's just no. This is how perspective works on a flat surface. Yeah.
Right.
We're told this is the 500-year-old proof of the flat Earth.
So on a football ground, for example.
Mm-hmm.
So I mean, all right. Okay. If this is different. Okay, misconception then. The curvature of a circle or a sphere, when you take a big radius, tends to be flat, right? That's what it is, right? But it's not flat. So it's kind of like measuring the curvature of a marble and measuring the curvature of a big, whatever, helium balloon or something. Then you will find it like much smaller. Right,
like an ant on a beach ball or something.
Exactly. So at this distance, especially of a football ground, or that is just not relevant. You can't measure, because the
but that's
the
not
displacement would be like much
that's
smaller.
not what I'm saying about that. No, I'm saying that this idea that as something goes away from you, it will go over a curve. Yeah, because you lose the bottom of it. Yeah, no, on a flat surface, yeah, you can actually repeatably demonstrate how just walking away on a flat surface, it appears as though somebody is disappearing below a curve. Yeah, but they're not. Obviously, they're on a flat surface. Yeah, I've done a couple of videos that show that effect. Yeah.
So I mean, right. Let's. We're next to Brighton, so I guess I have to say that. If we all go to the I-360 and then climb on top of the, take the big ride and go on top of it, why can't we see the Eiffel Tower?
Because we can only see a certain distance. We've got atmospheric effects that mean you can't see. If you live in California.
No, but okay.
Let me just give you an example. If you live in California, yeah. You get the weather report in the morning. You get, as along with the weather report, visibility, 10 miles. Yeah, it's not because of curvature or anything. It's because the atmospherics limit the distance you can actually see.
Yeah, but you could design some experiment where you have a laser and you shine it from the Eiffel Tower, and you could have telecommunication like this. Boom! You don't need to have satellites.
Well, you don't need to have satellites, because, again, we have line of sight communications, which, again, should be hidden by the curvature. Yeah, there was an experiment.
Yeah, so satellites do exist, right?
No. We have line of sight experiments with. There was an experiment in. There's a horrible video, a horrible documentary, but they used. I think it's called the convex Earth, and they got scientists from South America. They did an experiment where they were sending a Wi-Fi signal over a distance, I think it was 50 miles, where it should have been hidden. Now, this Wi-Fi signal is line of sight. Yeah, if it's blocked by anything, you won't get. Where
did the Wi-Fi signal go?
Sorry, they were beaming a Wi-Fi signal from one station to another. There's a frog down there. Beaming a Wi-Fi signal from one station to another one 50 miles away, right? The curvature should have blocked that signal. It's Wi-Fi, line of sight, yeah?
Well, it depends on which height did this...
Radio, it's line of sight. It can't go through the Earth. Yeah?
No, but it depends on which height you
they were doing
broadcast, right?
the height is taken into account. You can go online and get the Earth curvature calculation. One of the parameters you have to put in is your eye height. Yeah, so it's taken into account. Okay, I've got pictures of the White Cliffs of Dover from Calais or Boulogne. I can't remember. Boulogne, I think it is. Yeah, it's 31 miles away from the White Cliffs of Dover. Yeah, the eye height is 30 feet. Yeah, that's where the picture was taken. And with the Earth calculator,
the cliffs are way higher than that.
I know. But with when you
can you
plug
see the base of the cliffs?
When you plug those figures in, yeah, it should be 353 feet should be hidden. Yeah, the cliffs are 350 feet. Yeah, and yet from that picture you can see the base of the cliffs. You can see all of the cliffs. Yeah. What I'm saying, I'm not making stuff up here. Anybody, any of us can go out and do our own experiments. Yeah, plug in the figures into the calculation and see. No, I'm not supposed to be able to see that, but I can see it. There it is.
I think this is a different problem, right? There is one question is whether the Earth is round or not. The other is what is its actual radius. All right, I think I can and trying to measure the having like some actual numbers and figures that you put in those calculations, right, is actually quite complicated. It's not because the radius is so big, then you need to have like very precise instrument to do this sort of measurement.
Not really. I've got AutoCAD.
Well, what is the error on your
I've got
measurement?
AutoCAD. Yeah, I can draw up the Earth. The right size of the Earth in AutoCAD, and with AutoCAD you can measure.
Yeah, but do you know how, for example, if you take a picture, what is, say you take 1 meter stand like what we have in front, and then you want to take a picture of Calais. Do you know how much what is the exact altitude? Are you standing on some, something?
As I said, you plug in various. Parameters into the Earth curve calculation.
No, but I'm not saying you're making the calculation wrong. I'm saying the error estimation is wrong.
Well, there's no error in it. That's the problem. It's a calculation.
That's not scientific then.
We know how to calculate a circle. Yeah.
No, I know how to calculate. There's no problem. There's no problem, right? The problem is like if you take a stand and take a picture, right? What is the actual height at which you're taking that picture? That is very important when you're trying to make this.
And I'm trying to say, included in the calculation, right? I said 8 inches per mile squared. Yeah, that's the base calculation. But you can go online, and this Earth curve calculator, right? One of the parameters is what's your eye height, what's the height of the target, yeah? What's the distance of the target, yeah? And you plug that in, it tells you what should be obscured even from your eye height. Yeah? And, again, you can take that into consideration.
But what is the error on your eye height? Like, what is your error? Like, what is it, plus or minus 10 centimeter? Is it plus or minus 2 meter? Is it plus or minus, where are you standing when you do this sort of calculations?
Okay, when you do the calculations, you go to sea level, because as I said, most of
sea level, but you have tides, what do you actually stand on the beach?
Sea is level, no matter where it is, yeah? The sea, that's why it's called sea level, yeah? Water finds its own level.
Yeah, but
so if you go down to the beach, yeah, and you measure up from sea level, no matter what the tide is, yeah, because the water's going to be level.
The tide is the same opposite.
Right, it's going to be right. So you know the height above sea level, right? So then you can do.
So I would say there is at least 2 or 3 meter in errors in the sea level.
Okay, let's assume you're right. Let's assume you're right. 2 or 3 meters.
Yeah, but your eyes. What is your eye height? Right, the eyes is that. Sorry, I missed what your eye height. Yeah. Right, is 1.5 meter or 180 centimeters or something. Okay. Right, so the error is already bigger than what.
No.
Is that not true?
No, because as I said, you plug in the actual eye height. You measure your eye height above sea level. Yeah. That's one of the things you do to get the right value. Okay, you include the eye height okay, it calculates what that curvature
So your
should.
eye height is in between 0 and 3.5 meter.
It's
Because you have
in between-
waves and you can't measure exactly where you're standing on the beach, exactly like where is the actual sea level.
the actual sea level is where the water is.
You
Water,
have waves, right?
water finds its own level. Are you saying that
No,
I can't
I'm not
measure?
saying that.
I
I'm
can't
not
measure
saying
it.
that. I'm just saying that, you know, if you go, where do you stand on the beach? You know, where, like, it is like, all I'm trying to say is that there's like
Here's the
doing-
sand.
no,
here's
no,
the water. you measure from where
all
that.
I'm trying to say
water
is like for this sort of measurements, right, which are actually required to be quite precise, you need to have proper error estimation, the error that you're making on every single thing that you want to measure, right, that you're trying to measure, and that is how you're going to make it. And if you do that, well, I can guarantee you that you're going to find that you can see the over whatever you want.
Really?
Yeah.
So
You will find that is inconclusive, essentially.
yeah, no, that's what you're saying, yeah. But,
Yeah, I mean,
but as I said, we can go out. You can go out, and with you know, unless you want to do the scientific thing and fudge the figures, yeah, add in a constant, yeah, which you know, scientists will want to do.
Oh,
yeah.
I mean, we
Add in a
do
constant.
that.
Let's add in an error constant. And no, we can see.
The error constant is
No,
inherent into science, right? We can't do science if there's no error calculation. That's just
I'm sorry.
we have to have that.
If we have a circle, right, we have a point above the circle. You know, we have known distances.
I'm not saying that
There's no error. There is no
I'm
error.
not saying that AutoCAD is wrong when it's calculating the circle, the radius of the circle. I'm saying when you take you take your measuring tape, that might be a little bit wrong.
Again, water finds its own level. So where the water is at my feet is the same place the water will be. You know, that's why you get like you can test this with a clear tube. Fill it with water. Yeah, you sort of mark where it is. You know, in one place. Take the tube half a mile away. Yeah, it's going to be exactly the same place. Right? Water always finds its own level. Right? So you know, if I'm measuring from the water here, it's going to be the same wherever. Yeah.
Is there any other maybe any other questions you would like to ask each other as well? Maybe just draw a line for now.
I would like to address saying that you know, why is the Earth flat and everything else in the sky round? Yeah. Now Pierre said that you know, you've looked through the telescope and you've seen spherical objects up there. Yeah.
Mm-hmm.
Well, that's where I've got a problem, because you know, it takes two eyes to render 3D. Yeah. So if you're looking at something through a telescope, you can only see it in 2D. It's a blob of light. It's not spherical at all. If you see anything spherical with one eye, right, you're making that up. Seriously.
Right.
You can only render 3D with
how
two
would
eyes.
that look like then?
What I'm
How
saying
would that look
is a
like? We
blob
would
of
have
light.
to have like in this extreme, maybe this weird configuration where every single flat object that we observe is looking straight down at us.
I'm
at
not
the perfect
saying
angle, right?
I'm not
Otherwise-
saying things are flat. In the stars
okay.
and what we call the planets and whatever are flat. I'm saying they are lights. Yeah. Have you ever heard of sonoluminescence?
No. I haven't heard.
Sonoluminescence is when you pass ultrasonic sound into a liquid. Yeah. You get it at a precise frequency. What happens is bubbles, it's called cavitation, bubbles will appear and then collapse. And as those bubbles collapse, it emits light. And you literally fire this sound into water and you get a light shining like a star. They call it star in a jar. Yeah. It's not a round light or flat light or no, it's a light. Okay. So up there are lights in the sky. Yeah. And they're not spherical, they're just lights. But even if, you know, you categorically said no, they're spheres, you know, if you've got you're on a basketball court and there's lots of basketballs, you know, is the court supposed to be a sphere just because there's all these basketballs around? No, this is a special place.
No. This is different, right? We've made the basketball and we've made the tennis court, so that doesn't apply,
But
right?
somebody made
something
this place.
something which is mediated by, holds together with gravity is always wrong.
Sorry, gravity.
Oh,
That's another.
okay, right.
That's another topic.
Okay, yeah. I mean, go ahead, because I'm not sure. Because well, maybe I'd have to explain that. But on a flat Earth, right? If there is a gravity, then you're attracted towards the center of mass, and the center of mass is in the center of a disk. So it's like literally, in the center of the disk. And as you move, on the side, then if you're attracted towards the center, then that means the gravity starts to pull you, in a slanted way, essentially. So you'd have to like sort of climb towards. It'd be harder and harder to get to the poles, for example.
Okay,
That's
but that's only, according to a theory of gravity. Which theory are you talking about? Because it sounds very much like Newtonian to me.
yeah.
Right. Well, Newton has been proved to be absolutely, completely wrong. Right? Einstein came along and created a different model, not based on mysterious forces between two objects. Yeah, there's no mysterious force. Einstein says it's a curvature of space-time. Yeah. Now, both of these theories are there solely to allow this tendency of something to fall to the ground when let go. Yeah, allow that tendency to make it possible for somebody to stick on the bottom of a ball. That's the only reason there's these theories.
Stick in the bottom. I didn't quite catch.
Well, the question a child asks, the very first question, what about the people in Australia? Won't they fall off? Well, these theories of gravity are only there to allow, right, this tendency for things to drop when you let go of them, to allow for people to be standing on the bottom of a ball. Yeah, we don't see any evidence of gravity. Yeah, gravity is supposedly a weak force. The weakest out of all the fundamental forces, apparently. Yeah, overcome by magnetism. So, and
Sorry, overcome.
by magnetism.
But what does that
Well,
mean?
the standard experiment or demonstration of how weak gravity is that somebody will get a magnet and lift up a load of paper clips and says, well, this magnet is overcoming the force generated by the entire planet. Yeah. So it's stupid. It really is. Here's an experiment, okay?
But sorry, I didn't quite catch how that would make gravity.
Well, let me
a
give,
false force.
let me show you an experiment.
I mean, I think this is quite important, right?
Well, this is where I was going.
That something is weak doesn't mean it doesn't exist, right?
Okay, right. So a vacuum is much more powerful than gravity. We know that because Mythbusters did a show where they used a standard vacuum cleaner to lift a car. Yeah, just like the magnet lifting paper clips. Yeah, a vacuum cleaner literally lifted a car. That power of that vacuum only generated by a vacuum cleaner, not the vacuum of space. Yeah, was able to lift a car. Right. So we have a vacuum outside of this Earth, apparently, right? Which is.
But if you stop making the vacuum in this vacuum cleaner, which I think actually it might be, some sort of magnet which actually did that, but maybe
no,
I don't know. If it's vacuum, it's vacuum.
Yeah.
Maybe if you remove the vacuum, then doesn't the car go,
Yeah,
fall?
as soon as they switched the vacuum cleaner off, it fell.
Right. So
the point I'm trying to make is the vacuum generated by a standard vacuum cleaner, right, was able to lift a car on the surface of the Earth, where the gravity is strongest, yeah, easily lift this car, okay? Now we have a vacuum which is many times, orders of magnitude more powerful than the vacuum generated by that vacuum cleaner, yeah, acting on the atmosphere of this ball Earth, okay? So why isn't all the atmosphere dragged off into space? Because, whenever we see a high pressure next to a lower pressure, there's movement from high to low, always, yeah? So we've got a pressurized system, the Earth, right next to an unpressurized system, space, and no movement from one to the other. Right? There's no barrier in the way, apparently. Yeah, so there should be a movement, and the only thing that's supposedly stopping this movement is this weak force called gravity, which I've already just shown is overcome by just a piddly little vacuum generated by a vacuum cleaner.
I mean, this is something that you can try, right? Try yourself. Let's try. We can try on this table. We'll try on this table. Let's take a vacuum cleaner and let's try to see if we can lift it.
Well, if you see the Mythbusters
Let's
thing,
just see if we. I mean, this is something that we can do, right? Is this table heavier than a car? Yes or no?
heavier than a car.
Is this table heavier than a car? No,
it's not.
Right? So therefore, you need to have a weaker vacuum to actually lift it up, right?
Yeah. Okay.
So let's just take whatever vacuum cleaner and just actually try here.
No,
Do you think that this
we could
is
do
going
the
to-
same with a plunger. Actually, if we get a good enough seal on the plunger, yeah, put it on there and we'll lift a table. That's a vacuum. We create a vacuum with a plunger, yeah,
Yeah.
and it
But
sticks.
you
If
said
it's got a good
vacuum
enough
cleaner.
seal,
You said vacuum
it
cleaner.
doesn't matter. The vacuum
No,
cleaner,
no,
the vacuum
You
cleaner
said
is the
vacuum
source of the vacuum.
cleaner, right?
It doesn't matter where the source of the vacuum is, yeah. It's just a vacuum, a lack of atmosphere, yeah. You can create one with a suction pad, yeah.
Oh yeah.
Okay,
Definitely.
and that vacuum, that minute vacuum compared to the vacuum of space, will lift that table. Yeah, we'll even lift a car if you get a good enough seal. Yeah, that's what I'm saying. If you've got a minuscule vacuum that can overcome gravity here on a surface where gravity is supposedly strongest, yeah, why isn't it not sucking off all the blowing all the air into the vacuum? Yeah. So that we should be not being able to breathe right now.
Because, well, in a sense it is, right? Because the Earth gets thinner when you go higher, right? So
Yeah.
there's no movement of the Earth towards the space, but like the Earth, it's not like you get a straight, sort of like one time where it just becomes vacuum, right? It's like the Earth gets thinner and thinner, and then at the end it just gets
Okay.
nothing.
Let's go with that. Okay. So let's imagine this table's the Earth, and we've got the atmosphere here, and right now there's no vacuum attached to it. So let's say it's not thin. It's the vacuum. The atmosphere is like full strength up here as well. Okay. Now we apply a vacuum. Right. The molecules at the top start to go off into space, yeah, because they're right next to the vacuum, yeah. So they go off, and now you've got a lower level because now this lot's been taken away, yeah. So now you're down here, okay. Now this is next to the vacuum, that gets taken away, and this is next to the vacuum, and that gets taken away, and so on all the way down until there's no air left. Because as I said, even down here, a small vacuum will overcome gravity.
Yeah. No, I mean I don't know what is the thing. So if you want to I don't know what is the what is the reason for this.
Well, all I'm saying is I don't understand the model because the model does not make sense. You can't have a pressurized system next to a vacuum and hope to keep the pressurized system without having a barrier in the way.
Yeah, I don't know. I haven't thought of these questions.
Is there any other question that you would like to ask Dave on?
Yeah, I mean,
certain thing?
how? What about so okay? So gravity is weak, and then gravity is weak, and then we're not experiencing gravity. Is that what you're meaning?
I'm saying
I'm just trying to see what is the actual conclusion.
Okay, I'm saying that we don't have gravity, we have density and buoyancy. An experiment, the thought experiment I'll give you here is imagine if you had a gas bottle, yeah, an empty gas bottle, and you weigh it, and then zero out that weight, so the gas bottle is reading 0 on the scale, yeah.
No, you tell it.
Yeah, so you just zero it out, so you're ignoring the weight of the gas bottle, and you fill that gas bottle with 1 pound of helium. Okay, so it'd be filled with liquid helium, and you can measure it, so it's a pound. Yeah. Evacuate that helium, that pound of helium, into a balloon. Hold the balloon and hold a pound weight. If you let go of them, what's going to happen?
Yeah, it's going to fly.
Balloon's going to go up, the weight's going to go down. They both weigh a pound. They both have, this supposed force of gravity, exerting exactly the same. Just that one's less dense, one's less density space. Still weigh a pound. One goes up, one goes down. Yeah, it's density and buoyancy. Anything denser than the air will go down. Anything less dense than the air will go up. I've got videos of somebody taking an anvil.
What is that saying? Like, is that saying that gravity doesn't exist? What is it saying? Because this is gravity, of course, this is right? Like, balloon fly up.
No, I'm saying a pound weight just happens to be the helium. Yeah, it doesn't matter what it is. Yeah, it's just that the helium is less dense than the air. But it still weighs a pound.
Sorry, that's just
still weighs a pound.
That doesn't. I'm trying to understand what is the actual conclusion of this, because you're trying to give me some explanation. What is gravity, or you're trying to tell me like why is gravity so weak? But that doesn't explain me. What do you do? Like, does that explain us like how, if we go on to the poles of the Earth, we get like non-uniform gravity? No, right?
We don't see non-uniform gravity.
Yeah, right. Yeah? That's the reason. So that is a good reason why the Earth is not
It's just your model. Your model says we're on a ball, and it's gravity is pointing to the centre of the Earth, no matter where you go. I'm saying, we're on a flat plane. Gravity. There's only one down. There's only one down.
There's one direction, which is. And there's one predict like one sort of fundamental direction, which is down.
Yes.
Okay.
And it's governed because of density and buoyancy. Yeah.
Okay.
That's it. And if you went to the Einsteinian model, the Einsteinian model is a curvature of space and time. Yeah. So you have a massive object, and it's curving space, so that if you try and go past it, space itself is curving towards the Earth, say. And you try and go past it in a straight line, you'll curve towards the Earth, and that's why it's not really a force; it's literally a curvature of space. Yeah, well, that's really interesting. But what actually causes the movement? Yeah.
Sorry, what the movement?
The movement. No. Einstein's describing a curvature of space that says if you try and go in a straight line past the Earth, you're going to curve into it. Yeah. You're still going a straight line. It's just that space itself is actually curved. Okay, that's his model, right?
No, so you're going to be deviated. Like you're going to have a deviation from gravity, right? This is.
No, that's what I'm saying. They use an example of having a bowling ball on the middle of a trampoline. Yeah. And if you roll a marble next to it, in a straight line, the marble will start to curve towards, and it ends up sticking to the basketball, right? Great. But it doesn't tell you what provides the movement, okay? Because if you put if you're putting a marble next to, and you don't push it, you put the marble next to or near to the bowling ball, yeah? Well, in that model, it's actually gravity, the fact that we're on Earth and there's a downwards direction, that's providing the movement. Yeah? Well, I'm saying that Einstein's saying it's just lines of space. It's not telling you what's providing the movement. If I drop something, right, well, the lines of space say that, near the Earth, everything's going to point downwards, yeah? So if you try and do... But it doesn't tell you why it's going to move. Can you see what I'm saying?
Yeah.
It's telling you about how space is curved, but it's saying there's no explanation for the actual attraction or the movement. When I let go, right? Well, if I was to throw it, it will follow a line of space that way, yeah? But if I let go of it, what's causing the movement?
So the reason, right, okay. So this is actually quite a complicated question, and I think I know the answer.
Right.
The reason is because you are considering a 3-dimensional space, right? Well, 3-dimensional space, which is of course the reason,
that's
but
where
you
we
need to
live.
like, of course, but there is also time, right? And if you calculate the actual distance, right, including those 3 like dimension plus time, then you will find that it's not moving.
Sorry?
Because no, it is like it's a bit of it's a mathematical. Well, I don't know if it's right. It's so the right. So this you're referring as the fact that there is a curvature on space and etc. And then the light when it's shown, then it gets deflected, right?
Yes.
So yeah, I mean this is because we are thinking as time and space as being completely two different entities, and in fact, if you're calculating the displacements according to essentially the time and the space, then yeah, that quantity remains constant. So it's a bit of a mathematical, well, I would say trick, but it's just it is like that really.
Well, again, as I said, if you had the bowling ball in the middle of a trampoline, deflecting the trampoline down towards the bowling ball, yeah.
Mm-hmm.
Well, let's say it's in space. Let's imagine there is space, yeah, and that trampoline is in space away from the Earth, okay. So now there is no Earth pulling that marble down toward, yeah. If you put the marble next to the right next to the bowling ball, it won't move because there's no tendency to go downwards to make that marble move towards the. Can you see what I'm saying?
Yeah.
So Einstein's theory of space-time.
Is this trying to actually say that? Because I mean, we see stuff falling on the Earth all the time, right?
Yes.
So, what's the problem?
And gravity is just a theory to explain why people can stand on the bottom of a ball and not fall off. Yeah, that's all it is. I'm trying to tell you that these theories don't work. Yeah, the curvature of space-time, allows for moving objects going near something where it's deforming space-time. Yeah, a moving object will go towards it. Yes, fair enough. But if that object isn't moving, there's nothing in Einstein's model that will account for the actual motive force, the actual thing that causes the object to move. Yeah? Does that
So in Einstein theory, the object doesn't move. That's what I'm trying to say.
But I can grab your pen and drop it and it's moving.
Yeah, because it's because some time component.
Sorry?
It has, because the way you're calculating distance is different than the way Einstein calculated distance.
Oh, so I'm
It
only.
is actually
It's
this.
just so when I drop it, it's just an illusion because I've done my sums wrong. Is that what you're saying?
No, no. I'm saying the way you calculated the distance, which is probably X, Y, and Z, is just not the way Einstein calculated distance. He calculated with the time, and if you do that, then you will find that this one doesn't move.
Okay, well, I'm sorry.
No, but I mean,
I'm sorry. That's just blinding me with bullshit. I'm afraid because that makes no sense to me. I don't know if I've made myself clear on what I'm talking about. The lines of space time.
Yeah, I mean, Einstein theory is really complicated, and I'm probably not the best person to explain it. But I'm pretty sure that this is the way this was done. That you have to, if you want to talk about gravity and potential of attractions, then you have to actually take into account the time component.
Right. Well, shall we move on to something else?
Okay. Yeah.
Is there anything else? Any question that you want to really ask each other? That's something on your mind?
No, I'm.
So what else? All right. Okay. So we have this direction which is downwards. Where does this come from?
As I said, buoyancy and density. Yeah. Normally, if you get an anvil, yeah, one of those big metal anvils, yeah, and you let go of it, it's gonna hit the floor pretty quickly. Yeah. If you get a metal anvil and drop it in a bath of mercury, guess what? It floats. Doesn't go down. Yeah. Somehow it's.
But that's not a theory, right? Do you
somehow
agree that
the
this is
mercury.
no. Like you're getting examples, right, of what we see and we can observe, but that's not an actual theory of
Sorry,
why we stuff
I think
flowing
that's
going
what
down.
science is, isn't it?
No.
You observe stuff.
No, we observe
make-
things and then we try to explain it with some sort of mathematical concept. Why is stuff going down?
Not mathematical concept.
Or like
Mathematical
some
is
theory.
just a tool. What I'm
well,
saying.
it is.
What I'm saying is that I'm seeing effects. I'm giving you an explanation, right?
What is the
Density and buoyancy. Anything more dense than the air is going to go down. Anything less dense than the air is going to go up. That's it. You don't need a mysterious force or a curvature of space-time to explain it. The only thing, that you do need a curvature of space-time or mysterious force is to explain how people can stand on the bottom of a ball.
Okay. Yeah.
Okay.
I mean, yeah, but okay. Well, all right.
Next topic.
No.
I
I
guess.
mean, like. I mean, if people are satisfied with this sort of explanation, then I guess it's fine. But like, that doesn't still explain. That explains why stuff should float, right? Buoyancy.
Density explains why it goes down.
According to what? Like,
Well,
what is like? I don't understand. What is the actual force that makes us go down? That makes my pen go down?
It's not. Doesn't need a force. It's
What is-
density. It's just, you can see the same thing. If you get just a balloon with air, yeah, put it on water, it will stay on top of the water.
Yeah, but there is an actual equation that can calculate the buoyancy of something, right? A boat floats on the water.
Because of
balloon
density.
goes up.
Because
Right.
of density.
No. There is some actual mathematical concept that can say, oh, it's the pressure of the earth and the pressure of the water. Under
It's
the
the pressure of the medium
right.
around the.
Which is different, in the case of a balloon, from the top to the bottom and etc. And that makes it go up. But there's no theory that say what is this stuff making it go down, which is what gravity gives you.
Well,
right?
if you accept that a less dense object, something less dense than the air, will go up, then you've got to also accept that something more dense than the air
What,
is going to
so is it
go
because
down.
Right, let me try to continue then. So it's more the air is more dense on top, and then therefore it's less dense on bottom, and then that makes us go down, and then you can calculate like some sort of negative buoyancy or something.
It's
Like
it's,
how
it's more simple than your
No, I'm just-
calculations. Yeah, it's very simple. If you fill a balloon with water, yeah, and put it in the water, it'll have a neutral buoyancy. It'll just kind of float. If you fill it with a liquid like light oil, yeah, it will float. If you fill it with heavy oil, it will sink. It doesn't need calculations.
I agree with this. There's no problem with this, right? Like stuff floats on the water and balloon go up. There's no problem with this. The problem is, how do stuff stay on the ground? I just fail to understand it. I'm sorry.
Because that pen is more dense than the air around it. Yeah. Okay. So now the air cannot.
How does the air?
The air
change
cannot
this?
support it. Yeah. The air can no longer support it because it's heavier than the air. It's denser than the air. Yeah, I've already explained how heaviness doesn't come into it because a pound of helium and a pound of iron, will go in two different directions.
Okay, one more topic maybe. One more question.
Yep.
Do you want to ask Pierre one question or anything?
Well, not really, because the difference is I grew up in the same model that Pierre lives in at the moment. Yeah, I understand. I actually spent ages learning Einstein, because I thought it was real, so I know the model that you're living in, unless
that doesn't make, I mean, okay, that doesn't make you right. That doesn't give any credit to what you're saying, right? Like whether you know what I know or you don't know what I know. This is just let's just agree that this is just a rhetorical. And it doesn't really change anything. So, yeah.
Yeah. Again, I'm not saying I'm not trying to disparage you or anything. I'm just saying that I understand your model. So, so far nobody's actually come to me with something I've not heard before. Yeah, it's because we've all grown up with the same model. You know, we've all grown up with this. Yeah, and all I'm saying is, when you look at it, that model doesn't make sense. You know, you can paper it over with lots of calculations and mathematics, but fundamentally it doesn't make sense. Our senses tell us what this Earth is. Yeah, our eyes tell us it's a flat surface. Our senses tell us we're not moving. Yeah, and before anyone says, you should only feel acceleration. Well, when you're moving in a circle, that's acceleration. You're always constantly accelerating in different directions, so you would feel it. Yeah, we don't feel it. We're being accelerated in several different directions all at once. Yeah.
Except if this acceleration is really small and then you couldn't measure it, right?
Well, I don't know, 1,000 miles an hour, rotation of the Earth, 67,000 miles an hour around the Sun, 400,000 miles an hour being dragged along by the Sun.
No, those are big numbers, but when there's a big radius, that doesn't,
400,000 miles an hour.
Yeah, no, I mean, this
bigger than the radius of the Earth.
Yeah, I mean, and there is, 10 to 25 atoms in this stuff. These are big numbers, but that doesn't make it... That doesn't change the validity or something, right? So if a number is small, like if something is small or big, that's sort of irrelevant to like.
So you know what? If I'm sitting in a car and that car moves off at like 5 miles an hour, I feel it. I feel that acceleration. 5 miles an hour.
No.
2 miles an hour, I'd feel it.
So you're talking about speed, right?
Talking about acceleration.
Ooh, sorry, excuse me.
I think the fire's gone out.
I know. Got a blank.
You're talking about speed, but that's different from acceleration, right? The thing that you will find is going from 0 to 5 miles per hour, right? That's acceleration.
Moving around in a circle is acceleration. Yeah, moving at constant speed, in a straight line is not acceleration. But moving at a constant speed in a circle is acceleration.
Yeah, centripetal.
Yes, acceleration. Yeah, I'm telling you that we're moving, supposedly in this model, in several different directions, at once, accelerating in all of these directions, and we don't feel it. We can have a lake that's perfectly still. You can drop a feather and it'll lightly go straight down, while we're being hurtled in several different directions at once. So no, this model doesn't match our senses.
Okay.
Anything like to add before we sort of wrap up?
Yeah. Well, sorry. What I'm trying to say here is really that there is acceleration. All this, whether it's this is sort of connects towards to the actual fact that the Earth is round or not, right? The fact that we don't feel the acceleration, one explanation could be, and in this case is that the acceleration is too small at the point where we're trying to measure it, right? We can do that, right? Like if I'm in a car and I have something like accelerometer in my phone, and I accelerate very, very smooth, then I won't feel the acceleration, right? So this is one possibility, is that this is real, right? So we have to agree that like some of the science experiments that we're discussing here have very, very big scientific bias and errors that you need to take care of. But that you need to take care if you want to actually calculate what is the actual acceleration at which we should feel, because we're doing this, and there's the Coriolis force and etc. So this has been observed in the for climate and for weather. But those experiments are interesting because we the person who is measuring it, or who is measuring these sort of things, has to take care of the uncertainties. So whatever you're measuring, whatever is been it's not about the radius of something. Radius of something is that's everybody knows. All those equations. People know exactly what is the, you can know exactly what is the radius and the curvature, etc. But what you're using to measure, that can be a little bit wrong. And I'm sorry, and having and making mistakes in those measurements is, somehow it's a different answer than answering whether the Earth is round or not, right? So it's are you trying to if you're trying to measure the actual acceleration, then you need to have a very precise apparatus. If you want to prove that the Earth is round, is round, then maybe you need to have a less precise apparatus, right? And the fact that you can't see further away, the fact that if you see, we've discussed about this already, but these are different questions in science, right? Trying to measure the radius of the Earth and trying to determine whether the Earth is round or flat. That's, in a sense, that's a very different question. So, yeah, we should be careful about that. That's kind of what I want to say.
Well, you also mentioned the Coriolis force, which is interesting because it's not a force at all. It's an effect. Yeah, it's like you get two kids on a roundabout, yeah, being spun around, yeah, and one kid rolls a ball to the other, and that ball appears to the other kid to make a deflection to one side, yeah, but it only appears to it because if you're looking from above the roundabout, yeah, that ball is going in a straight line. There's no force being applied to it. It's just the appearance of that ball to the people on the spinning system. There's no force, yeah. So the idea that this Coriolis effect, yeah, can change the direction of hurricanes, yeah, it's a lie because there's no force involved. It's just an effect, and they just made this idea of a force, calling it a force, so that it might sound like it will affect the course of hurricanes. Yeah, that's it. We don't observe a Coriolis effect. They say that snipers have to account for the curvature of the Earth. Because of not curvature of the Earth, but the movement of the Earth, yeah, because it would deflect the bullet one way or the other. But no, we don't see it. The only reason that bullets sometimes do follow a slight curve is called the Magnus effect, which is bullets are fired from a rifled barrel, which make the bullets spin, yeah, and when a spinning object is moving through air, it'll be deflected. Just like David Beckham can kick a ball and put spin on it and allow that ball to curve around in a circle, in a nice, neat curve.
But
yeah?
Those effects could happen, once again. The fact that this effect exists doesn't really change the conclusion whether the Earth is round or not, right?
That particular thing tells whether the Earth is moving or not.
Well, sorry, moving or not.
Yeah, well...
this sort of thing could happen, right?
Well, you get the Magnus effect curve.
If the acceleration was small enough so that you couldn't see it at a distance of...
You get the Magnus effect curve. It doesn't matter which direction you shoot in. You would only get this Coriolis effect if you shoot north or south. It's only north or south when you get the deflection.
Yeah, so you can get both, right?
Right, but I'm saying Magnus effect will occur no matter which direction you fire in. Yeah, you don't, and it works the same no matter which direction you fire in. So you don't get any kind of increase when you fire north or south, right? Planes, right, don't have to fly north to go west. Yeah, to take into account of this, the Earth is moving. Yeah, so no, it's sorry, I know. Yeah,
I think we're all freezing a bit. But anyway, thank you so much for both of you doing this. I think, like I said earlier when I first started the podcast, I really do appreciate that you have both come forward with obviously alternate approaches to whatever this is, and I think it's going to be a great insight into people, so people can really sort of just, even if the listener at home who's listening to this or watching whatever, just one thing that on both sides have said, they just go and do a little bit of research themselves, and then from there they can find their own truths. So I want to say thank you so much for both of you for doing this. I really do appreciate it.
Yep, thank you.
Thank you very much. It was very interesting to talk with you.
Thank you.